Hi, good evening. My name is Mr. Mlinga. Today we'll be looking at separation techniques, and in particular we'll be looking at chromatography. There are quite a lot of separation techniques that we have that we can use, but today our main point of focus will be on chromatography. Now, chromatography, there are quite a lot of things that we need to know. Among them, the things that we need to know are, one, we need to know what the chromatography is all about. We need to know the principle. We need to know the types. Now, before we go to types, it's important that we need to look at the use, and then we can go to categories. Yeah, among others. So these are a few things that we need to focus on, even as we try to look at chromatography as one of the important separation techniques. Now, to start with, chromatography is one of the most important separation techniques that we use in labs, in analytical labs. Why? It's because it has got some features that enable us to perform certain activities. Yeah, it's because of some features that it has. But regardless of, maybe let me now look at the principle. Regardless of the type of the chromatography that you want to be using, there are two important things that are present. Let me look at two important features of chromatography. One, there's what we call a mobile phase. And then two, there's what we call stationary phase. These two phases, as the features, one might put it, are very, very important. Are very important because, one, they help us to determine the type of samples that we can work on. Two, they can also help us to categorize, to put these chromatography in categories. Yeah, it is because of these two phases that we have. Now, when we say a stationary phase and when we say a mobile phase, what do we mean? I'm going to leave it here. I will have to go to the uses. Where do we use chromatography? Chromatography is a separation technique that we use in analytical labs, even in other science-related fields. When do we use? We use it, one, to determine the composition of the components in a mixture. Yeah, we can use chromatography to do that. We can use chromatography to determine the composition of components. Is it making sense? To determine the composition of a mixture. It's not making sense. Let's just say to determine the composition of a mixture, things that are present in a mixture. We can use chromatography to isolate them. One, to quantify as well as to tell its quality. You can do it for qualitative as well as quantitative analysis. We can also use this separation technique called chromatography to determine the fake, the counterfeit, yeah, fake products. We can use chromatography to determine the fake products. Why? Because when a product is made, there's a formula that indicates the amount as well as types of things that are present in the product. So now when someone comes with a duplicate saying, this is also a product that I've made, the one thing that we can do is to compare the products that are in this one, which is certified, as well as the one that has been brought. We can compare, and then if you find that the one that has been brought is lacking some important ingredients, then you can say this is fake. Or if it has more than the one in the actual one, then you can say it's fake. And of course, a lot of methods that, a lot of things that we can use this chromatography for. I've used it for quite some time, and some of these things I'll be speaking out of experience. So yeah, I think that's the first thing that I need to know where it's used. You can also look up to other uses of chromatography. Now, maybe let me just refer to some things that are written here, where it says some things will be referring them to the notes, and at times I'll just be speaking from the information that I have with me. As I said, chromatography is an analytical technique that is used to identify the components in the mixture or separate the components from a mixture. Exactly, that's what I said. Now, we're saying that, of course, there are quite a number of types. Some things I'll be just box like that. Yeah, of course, there are some. Now we're saying that there are quite a number of types of chromatography that we can know, and then the types are based on these three things here. If you remember, I'd mentioned them. Okay, where are they? Oh, they're here. We're saying one is the mobile phase, the other one is the stationary phase. So this has been brought out. Now, how do we really understand when we say mobile phase, when we say stationary phase? One thing that we need to know is that for samples to be separated in a chromatography, that sample that we have has to be placed somewhere, and then there must be a solvent that is taking it, or that sample that we want to, that mixture that we want to identify the components therein, it has to dissolve. At some point, it has to dissolve, and when it dissolves, it has to be taken by some fluids, some solvent. Yeah. So the phase or the solvent that is taking the mixture, splitting it into different components there that are in there, that's what we call the mobile phase. Yeah, and then that thing which is moving supposed to have some part where it is some part where it's positioned. That's what we call a stationary phase. Let me give you a practical and from a high school science how we can understand, we can put a full understanding of mobile phase whereas stationary phase. Allow me to close this part. Let's say I want to identify the components that are in the colors that are in ink of the ball pen. How can we do that? And this is the best that we can do. So what we need to do is we need to have from high school, I believe you're able to recall, you need to have say for instance, we have this paper which we call the chromatogram. And then we want to put this in the beaker, And you know that most of the solvents that are used are volatile, so it's important that on top you close. Okay, maybe this thing is not nicely drawn. Just allow me to have it drawn in the best way. Let me just draw it here. Say for instance, we have this as our Let's try here. We have this, oh, not this one, not this one. I want this one. Okay, suppose this is our chromatogram. This is a paper where we want to perform the chromatography. And then we have a vessel where we put this thing. Okay, let me just change the color. And then we have this thing where we're putting the solvent, and then we're going to have an initial line that you need to draw. This is from high school. I want to just remind you of the stuff. Okay, this is an initial line, and then I'm trying to explain on the mobile phase as well as the stationary phase. And we know very well that the initial line has to be drawn underneath. The level of the solvent has to be underneath the initial line. Now, so for instance, in here, you want to identify the components that are in here. So we have component and that component. We want to identify the things that are present in here. The things that are present in here, so we can have component A and can have component B. We want to identify how many components are in there. Now, remember, in here, we have the solvent. We need to have a solvent. So in this case, the solvent, once this paper is dipped in, and know that this paper has to be porous. So the moment this paper is dipped in, the solvent will start moving on the paper. You see, it's the solvent which is moving. So in this case, the solvent becomes our mobile phase. Solvent is our mobile phase. Now, where is this mixture moving? This mixture is moving on the paper. This mixture is moving on this chromatogram, a paper. So on the paper where you put a sample, it depends again on the types of chromatography you are performing. At times, this paper A can be aluminum foil coated with silica gel. Okay, of course, that becomes now thin layer chromatography. And then at times this paper A can be used just as a paper, not just a filter paper. It becomes, yeah, of course, paper chromatography. Now, what I'm saying is that these samples are put on this substance A. So the substance A, where the solvent is taking, is moving together with the solvent, that's what we call stationary phase. At least now I've explained which one is stationary phase and which one is a mobile phase. Yeah, these are the things that we need to know. These are the things that we need to know. So that is the point where you were saying the stationary phase as well as the stationary phase as well as the mobile phase. Now we're saying that these are some of the classes of chromatography that we have. Now I'm going to give you a very easy way of distinguishing one type from the other. So far, they have given 4, but of course, some of these will go and be splitted into other types. Those other types be splitted into other types, just like that. We have quite a number of them. So the ones that have been put out here are these ones here. So we're saying the first one. So we're saying that the classification of chromatography is based on the state of the stationary phase. So saying the physical state of the mobile as well as the stationary phase will give rise to the 4 types of chromatography. So the first one that we have here is liquid solid chromatography, but you understand very well. Remember what I was saying, that the solvent that carries the sample, the solvent, or the other term that I used was fluid. You know, when you hear the word fluid, we're talking about gas and liquid. So the type of the fluid that you are using to carry the solvent will give rise to its name. So if the mobile phase that we're using here, so now I'm trying to give the clarity. If the mobile phase that used in here is a liquid, it's going to be called liquid. And if a stationary phase that used is a solid, it's going to have that combination of liquid solid chromatography. So liquid solid chromatography. So the liquid here is the mobile phase, in case the question comes like that. So this is the mobile phase. This is the mobile phase. And then the solid is the stationary phase. And we understand very well that a solid cannot carry cannot be carried on top of the liquid. It's not making sense. It's a liquid that has to slide on a solid. Yeah. Even if you have a liquid somewhere there must be a solid where that liquid is being kept. Now we have a solid here, and then on top of the solid, that's where the liquid is sliding over, carrying the sample, splitting into different components that are there. Then we're going to have that class. Liquid, solid chromatography, it tells us that the liquid is a mobile phase, and then the solid is a stationary phase. Something can be applied here. Now here we've got both of them are of the same physical state. So we have liquid chromatography, and I'm going to explain on how each one of these is used and how to determine which one is the best method to use. And then we have another one, gas liquid chromatography. So what that means in here is that you need to have the liquid, we need to have a moisturized environment, okay, along the column. I'm going to explain the column. That column, inside of the column, has to be moisturized, of course, by some special solvent. That is the liquid. And then we're going to have the inert gas carrying the samples. Okay, again, the type of a sample that you want to determine will also give rise to or will give you the prediction of what type of a chromatography you're supposed to use. And then we also have a gas solid chromatography. So these are the 4 types of gas solid. These are types of chromatography that we have. But by the way, this thing here will also be classified into other types. Yeah. Liquid solid, the one that I was just drawing here, where we had 2 samples A and B, then we had the solvent, the beaker being covered on top. Yeah. So once you have that one, that is an example of a liquid solid chromatography, because we had this liquid that was carrying the sample on the chromatogram, and then the paper where the samples were being positioned, that is a solid. So the one that I've drawn is a practical example of a solid liquid chromatography. However, the type of a solid that you use will also give rise to the type. You see, that's why I said some of these types will go and be splitted and get subdivided throughout like that. It depends on the level of education as well as the course that you're doing, because certain things may be studied in a detailed way based on what you want to achieve at the end of the day. So if the solid is a paper, a filter paper for that matter, we're going to call it a paper chromatography. You hear that? If the stationary phase, or maybe let me put it this way, if the stationary phase that you use, stationary phase is a paper, we're going to call it paper chromatography. We're going to call it paper chromatography. We're going to call it paper chromatography. If the stationary phase you use is a paper, of course, knowing that a solvent has to be there as a mobile phase, it's going to be called paper chromatography. And should we use aluminium foil? Now this sounds like Chinese, aluminium foil. I know when you buy Blue Band butter, there's that thing they see on top. That's a practical example of aluminium foil. Now, you see that aluminum foil cannot allow water to run through it in an ascending way. So they apply what we call silica gel. So silica gel is the one that has got highest affinity to attract water to run through it. So when you have aluminum foil coated with silica gel, being the stationary phase, this is going to be called thin layer chromatography. These are some of you things that need to know that when you use a stationary phase under liquid solid chromatography, if the solid used, the stationary phase is the paper, we're going to call it paper chromatography. Most of the time, the paper that they use is a filter paper. And then at times you want to have an advanced way, especially when you have the UV machine to, at an advanced level, we use aluminum foil, and that aluminum foil is coated with silica gel, being the stationary phase. Then that type of liquid solid chromatography will be called thin layer liquid chromatography. They like abbreviating it, thin layer chromatography. If you want to sound more educated, you can say thin layer liquid solid chromatography, but it's just one and the same. So that's what this part is saying. But there's this point here, I would say that in this module, we'll concentrate on the gas liquid chromatography, since it's the most important type of a chromatography that is used as a separation technique. I was just trying to dramatize on that part on top because these are some of the things that you need to know. I saw there was a question which was talking about identifying which one's the stationary phase and identifying which one's the mobile phase. That's why I took much of my time in trying to labor on this part here. But as the point indicates that this time around, we're going to focus much on the gas liquid chromatography. Now, remember, it being a machine, you cannot have a machine which is just a liquid. Of course, all the machines must have some solid stature at some point. Yeah, but why is it that the stationary phase, the part where the gas will be moving is the liquid? Why? So we have to look at how that is done. If you have questions, you can reach me on this number here. Okay, +26097 5578 694. You can reach me on that number, then you can chat at length. Okay, we move on to the next slide. Like I said, certain things, I'll be referring them to this, and then at some point I'll be speaking things on my own. So we're saying that the gas liquid chromatography is a type of a gas chromatography in which the substance to be separated are moved by the inert gas. It's a very important point here because remember we said that a mobile phase is the one that moves the component you want to separate. So we are saying that, look at here, look at here. Maybe let me just end here. So you're saying that the components are moved by the inert gas. So the gas is what moves the component, and that gas is a mobile phase because it's moving. Yeah. Now we're saying that it's filled with a finely divided inert solid coated with a non-volatile substance. Okay, we're going to look at this at a detailed stage, and saying each component migrates at a rate determined by its solubility in the stationary phase and its vapor pressure. Let me just read it through and then I'm going to explain. Yeah, vapor pressure, and then I say gas liquid chromatography is a useful separation, is useful for separating ions, molecules that are dissolved in a solvent. Good. What do they mean? What do they mean? What they mean is, let me cover this start, and then write a few things here. So what the meaning is that in here, you need to have, now let me explain how components are separated. How components are separated. I have to explain. I have to explain. What it means is that in here we're going to have what we call a column. The column is moving from, okay, I have to give you a structure of the machine so that you understand. There's what we call a point of ejection. You need to have a point somewhere here where you introduce your sample using a syringe. So you introduce your sample in a very small quantity. You introduce it in here. Now remember, along this column here, we need to have coated with a substance, but remember this thing, there's a little bit of heat that is involved in here. So what happens is that we're going to have some vapor around the walls of the column. We're going to have some vapor along the walls of the column, and then this side here you need to have a detector. I think I will have to look for the instrumentation so that I explain it better. You need to have a detector this side, and then what happens is that when you introduce a sample from this point, this sample will come in contact with this vapor around here. It will come in contact with this vapor. But remember, it says how long it takes from the time it is introduced in the machine up to the time it's being detected by the detector depends on one, the solubility. I think that's the most important thing of it all. Solubility. There are some people that I hate moving with. You're moving with this person along a certain place where he knows a lot of people that know him. He'll be like everywhere greeting. Hi, my friend. How have you been? I'm sure you can relate. Hey, boy, I'm Kudala. So where have you been? Come on, man. We are on a journey. We're going very far. This guy is greeting everyone that he finds. And then we have me who minds his own business. What am I going to do? So the moment this sample comes in here in form of a vapor, because remember, even if you introduce this in terms of a liquid, because of some temperature around, it's going to be turned into a vapor. So what happens is that those components, some will be interacting with the walls. They'll be dissolving in the solvent along here. While me, who is just minding his own business, I'll just move all the way up to the time I get to meet the detector, and then the detector picks up to say there's a component which has come. Well, these guys that are busy greeting people everywhere, by the time they reach here, me, I've already gotten there. So you can have one pick for the one that arrived first, and then the other one for the one that arrived later. Yeah, and then you're able to interpret the magnitude of the peaks, the height, and all that. Then you can tell. Once you see these two peaks, remember we said we can identify the types and the amount. So types, how many would be dependent on the number of peaks that do display on the screen, of course being transmitted from the detector, and then the amount will be studied based on the interpretation of the peaks. Yeah, unfortunately, don't do spectral method of analysis, most of them, the IR, UV, and all that. But a partial interpretation of the spectrum, maybe we can look at it so that we have a full understanding. So that's how it's done. This is a column here. You need to have a column. Along the column, there's some solvent, which is a vapor. Remember, we're looking at gas liquid. So the stationary phase here, you need to have some vapor or some solvent, and then we introduce the sample, and then the sample will be carried by an inert gas. Why can't we use another gas like oxygen? Why can't we use it? The reason is because if we use a gas which is very reactive like oxygen, it might end up reacting with a lot of these components that are in here. And at the end of the day, you form a complex. Let's say you have carbon in here. Carbon is able to react with oxygen, and then you produce carbon dioxide, which you did not intend. In case you had hydrogen, reacts with oxygen to form water, and then water mixes with this solvent here. It might not even reach the detector. So these are some of the things that you need to understand about gas liquid chromatography. The thing you didn't know is that the gas is a mobile phase, and then the liquid is the stationary phase, and that liquid is positioned along the walls of the column. So I'll just be going to those points that I highlighted because these are the ones that I feel are of great importance. Now, of course, there are quite a lot of terms that associated, such as ion exchange, the partitioning coefficient. Some of those terms you're going to find them later. Partitioning coefficient and all that. So the second point is this one, which is highlighted here. It says, as a sample mixture moves through the column, that's perfect. I'd used the word column, and I just demonstrated where the column is found and why do we need a column. It's a very small thing, but as a whole, it's very small. And one thing that I have to make mention to is that the efficiency of gas liquid chromatography, it depends on the length of the column. Because if the column is very short, you find that some 2 or 3 components will reach the detector at the same point. So you need to make sure that we increase the length of the column so that by the time the sample reaches the detector, they might have been splitted into different components. So I'm saying moves through the column, and then the sample that interacts strongly with the stationary phase spend more time in the stationary phase versus the one that is moving fast. That's what I said. Greeting everyone that this guy finds. Hi, hello, start talking about how the holiday was and all that. While the friend is going. So the one who doesn't interact much with the walls of the column, you're reaching the detector area and all that. Now, there's what we call retention factor. The retention factor is of course, though we don't use much of it in here, we use much of it in thin layer chromatography, as well as paper chromatography. But retention, just the retention itself. Allow me, to talk about the retention factor. There's retention factor and retention time. The retention, we're talking about the amount of time that the sample spends from the time it is injected into the machine up to the time it reaches the detector. Remember what I just said? Maybe I can just go back in here, that the moment the sample is introduced here, we can detect the time, and then we see the time that a peak is observed on the screen. So the amount of time that this sample spends within the column, that's what we are calling retention time. Yeah, that's basically this point there. I say. So I'm saying that yes, that's what you're saying. And the symbol that we use for retention being the time, we use that one. But if we're talking about retention factor, you use capital F or RF, capital R and then small f, retention factor. We're talking about thin layer chromatography. We don't talk much about just retention. We go to retention factor. So I'm saying while polarity is usually the major factor governing separation, the boiling points of the components of the sample, also play a role in determining the retention time. Components with higher volatility with lower boiling points tend to spend more time in the moving gas phase and therefore have a shorter retention time. So what we are saying is that some of these components may be in solid form. I talked about a little bit of the temperature within the column. Some are able to boil. Yeah, once they boil, they change into a gas, are able to change its states. Yeah, it depends on the boiling point and all that over the component that you are separating. But there is an important word that has been used in here, which is called what term is that? I just saw it not too long ago. Which one is that? Oh, right over here. Again, I've missed it. Where are you, my friend? I saw the word polarity. Polarity. Where are you? Can't find it. Oh, here. They're saying that there's this word that they've used, while polarity is usually the major role. Now, when you say polarity, we're talking about these samples. There are some that there are certain samples that are said to be polar, and the others are non-polar. Now, the polarity of a sample, especially a solution, may not be understood easily, because you have to do a little bit of structure elucidation. How are the atoms positioned in this compound, or what's the dipole moment, the bond order, and all that. Yeah, maybe let me not talk about it, because you may not have some information like the bond order, the dipole moment, and all that. So just know that some substance, polarity and solubility, they are one and the same. Let me just leave it that way. Yeah, polarity and solubility are almost the same. So when you hear of the solubility, they're talking about the substance. If both of them are polar, they're able to dissolve. And if they are not polar, one is polar, the other one is polar, they can't dissolve. So remember what I was saying, that the number of peaks that are detected will be dependent on the number of components that are in there. So this is how the peak appears to be, and then you're able to see. But remember, at times there are times when the solvent you are using, the solvent, not the mobile phase, the solvent. Remember, the stationary, the mobile phase is an inert gas, but at times the solvent used is able to reach the detector, and you can see this one here. You're able to tell that this peak, I think it's that of the solvent. Yeah, so all these things, they have to guide you when you're in the lab, how to interpret the peaks. Though the peak, they are somehow similar to that of mass spectroscopy method. Injection of the sample from the column, the one that are drawn on the left. A very small quantity of the sample is injected, because we're just trying to determine the types. We don't need a lot, especially if you're using HPLC, high performance liquid chromatography. Of course, the amount that you put there is of great importance. I'm saying very small quantity of the sample that you are trying to analyze are injected into the machine using a syringe. That's a syringe. I think that's what I said. It has a needle. Now that needle has to pass through the rubber. Let me just draw it here. The time of injection, the point where you inject your sample from, there is a rubber here. Why do we need the rubber? It has to seal. Because if we don't seal here, instead of the sample going to the detector, remember we're saying some of them are able to boil. It was a liquid, turns into a gas, and then it escapes. At the end of the day, you don't do anything. So make sure that there's a rubber here, and then the needle of the syringe passes through there just to introduce the sample in here. And then the moment you pull out the syringe, the needle, the rubber seals off, so that we don't have a sample coming back from the point of injection. So I'm saying that the injector is a container in an oven. Why do we need an oven? A little bit of heat to produce that vapor, whose temperature can be controlled. Of course, we have to control the temperature, okay? It is hot enough so that all the sample boils and is carried into the column as a gas. That's what I said. At times we may have a liquid being introduced there as a sample. So now the liquid that you have will determine the temperature. We're saying the temperature is controlled. So the liquid that you put in here, if they say that liquid has a boiling point, which is 75 degrees Celsius, meaning you cannot set your machine at 50 degrees centigrade, because that sample is not going to evaporate. That's what that point is trying to emphasize. Now we're saying that how the separation works on the column. Remember what we said? The column, the walls of the column is got some vapor. which that vapor is in, not really vapor, but moisture, I would say. Yeah, that moisture, which is in the liquid, because the liquid, gas liquid chromatography, our liquid is the stationary phase. Yeah, so we're saying that one of the things that might happen to a particular molecule in the mixture upon being injected is that one, it may condense within the stationary phase. These are some of the things that you are likely to find. You inject, especially if the temperature is low, you inject that sample, solid liquid sample doesn't vaporize. It's not gonna reach the detector, just, and all that. Or in case there's a blockage on the column, that leads to the detector. Of course, this thing, the gas that goes in there with low temperature, you find that it's able to condense and all that. I'm saying that it may dissolve within the liquid, or within the liquid. At some point, you may find that this sample dissolves within the liquid. And we're saying at times it may remain in the gas phase. Yeah, these are some of the expected sources of errors that you're likely to encounter when you are in the lab. So we're saying that a number over here now, just those highlighted points, we're saying that a compound with a boiling point higher than the temperature of the column will obviously tend to condense at the start of the column. That's what I said. I was just giving you an example of a sample boiling at 75 degrees centigrade, and then you set your temperature at 50 degrees. If it is boiling at 75 degrees centigrade, changing from liquid to gas, meaning when you introduce this sample, even if it is in gas form, the temperature being set at 50 degrees centigrade, even if it was a gas, it will condense back to a liquid because the temperature in there is lower than the boiling point. That's the meaning of this point. Then the other point here says that similarly, some molecules may dissolve in the liquid stationary phase. Some compounds will be more soluble in the liquid than the other. Of course, the difference in terms of solubility gives rise to the differences that are exhibited the time when the samples are being detected by the detector and the time when the peaks appear on the screen. That's what this point is trying to say. So yeah, some are more soluble than the other, and they tend to spend more time in the stationary phase, being absorbed, delay, greeting one another, explaining how the elections were in Dundumwezi and all that. Well, the other guy is just going direct to the detector, and then you get to have the results. So we're saying that, I hope I'm not too fast. The process where a substance divides itself into two immiscible solvents, the process where a substance divides itself between two immiscible solvents because it is more soluble in one than the other is known as partition. Wow, we've started learning now. That's a point that I'd said earlier. Partitioning coefficient, and all that. So we're saying that there are moments when the substance divides itself between two immiscible solvents because it is more soluble in one than in the other. It's called partition. Let me close here and then explain more about the partitioning coefficient, because that's my job. Okay, so let's look at, this is even bringing me to one of the separation techniques that we will have to look at. Suppose we have, this is a beaker. And then in this beaker, we have two solvents. Let me use different colors. We have two solvents. We have this solvent here. And that's a label, first label. And then we have another one here. Or maybe that one is not very, very visible. Let me try to use a different color. Can I use black? I think so. Okay, not that done. Okay, so we have okay, so we have that one, and then we have another one. We have two solvents. There's a solvent here. There is this solvent here. I'm trying to undo. Oh no, now I've undone everything. Okay, where's the black line? Where are you? Black line, where are you? Oh, there is. Yeah, so in case we have the solvent here, and then also I'm trying to explain on the partition coefficient, then we have another solvent here. Let's say this is oil, and this is water, oil and water, oil and water. And then what do? You bring in biscuit. It's a practical example I can give you, biscuit. And then this biscuit, how is it able to dissolve? This biscuit, is it dissolving in the solution here? Is it dissolving in water? How is it also dissolving in the oil and water? So find that this biscuit is likely to divide itself depending on the solubility. Yeah, you find that to dissolve, maybe to dissolve more in water and less in oil. So the way it divides itself into two liquids that do not mix uniformly, because liquids that do not mix uniformly are the ones that we call immiscible. So the way this solution, or the way this sample is dividing itself within these two immiscible liquids, that's what we are calling coefficient, partitioning coefficient. Partitioning coefficient. So this is the part which is here. So this is the part which is here, the partitioning, saying that the process where a substance divides itself between two immiscible solvents because it is soluble in one and less in the other, like the way I said, water and oil. That is what we are calling coefficient, partitioning coefficient. Yeah, partitioning coefficient. So that is, so you can say that, maybe just look at this point here. Oh no, not this one. I'm supposed to get the other one. Which one am I supposed to get to highlight? Oh, I'm supposed to get that. No, not white, maybe red. Yeah, so we're saying this side that you may say that a substance petitions itself. Petitioning is more or less like dividing, like the way you buy a computer, then you need to divide the internal storage. You put them into different partitions. I hope you understand the petitioning of an internal storage of a computer. So I'm saying the substance petitions itself between two liquids. There's one which is a stationary phase, then the other one is a mobile phase. Yeah, that's one way in which that can happen. You have a mobile phase, which is a gas, and well as the stationary phase, which is a liquid. So we're also likely to have such challenges whereby this substance can dissolve partly in a liquid and less in a gas, or more in a gas and less in the liquid. That's the coefficient, that's the partitioning they are talking about. Okay, some of these things I just ran through them. Now we're saying retention time. I think I talked about this RF value, which I said is mostly common in thin layer chromatography as well as paper chromatography. Now, there is a point that I like bringing out in a dramatized way to say, if mom and dad are going to the market, and then you say, mom and dad, I want to go with you. Of course, the one who's driving could be dad or could be mom. Now, there can never be a point whereby you as a passenger, you get to town earlier than the vehicle and the driver. It's not possible. What do I mean? When you're going to town, let me speak of a bicycle, because maybe talking about a vehicle, someone would say, no, I dropped off the vehicle and then I got a bus. Now, in the village, the only quickest mode of transport that you have in there is a is a bicycle. You're on the bicycle, and the one cycling is always seated in front. There can never be a point where the one cycling a bicycle where you as a passenger, you get to the destination earlier than the one cycling a bicycle. It's not possible. It is either you reach together, and you cannot reach together. Yeah, either you reach together or you reach, the person cycling the bicycle reaches earlier than you. Maybe you remain on the way. So speaking of a chromatogram, when you have a chromatogram here, we have these items, this one here and this one here, being analyzed. Then when the solvent, remember we said that the solvent level is always underneath. If this is a solvent, that is our solvent. Now what's going to happen here is that when the solvent starts running through this paper, it finds this dye, the solvent is not going to wait for these substances to dissolve. The solvent keeps moving. And then these guys will start coming. But there will be a point where the solvent says, because it's going against the gravity, says, I cannot go any longer. These things here can never be at any point go beyond the level of the solvent. It can never. So I'm saying you as a person who's a passenger, you cannot get to the destination earlier than the driver. It's not possible. So there are only two things that are likely to happen. Number one, it's either the solvent moves the same distance or it moves less. So this is what brings about retention factor. Retention factor. Retention factor also is dependent on the interaction between the sample and the wall of the filter paper. So we're saying that there is a time taken for the particular component to travel through the column to be detected is known as the retention time. This is retention time and not retention factor. The one I'm from explaining on is a retention factor. Now, to do with a column, it's called retention time. And the symbol that we use is, I think it's TR. Is it RT? Yeah, we'll see. No, I think, yeah, we'll see. We'll see which one is which. So yeah, so they're saying that the time it takes for the component to be detected, that's retention time. This time is measured from the time the sample is injected into the column up to the time the maximum peak of the height of the compound is observed. So it's that different compounds have different retention times. For a particular compound, the retention will be dependent on these are things that where the interaction of the compound depends on. One, I think it's just a repetition of what we had already discussed. One, we're saying that the temperature in the column. Two, the solubility. How is the sample dissolving in the stationary phase? The other one is the boiling point. Of course, these points we have already exhausted them. It depends on the temperature of the column, depends on the stability, as well as the temperature and the boiling point are one and the same thing. Though we can split them, say the temperature within the machine that determines how it must evaporate, or the boiling point of the sample. These are some of the things that would delay even the results. You know, because there are times we're working under pressure, you need to produce the results. Let's say someone brings you the sample to say, no, I'm trying to start up a machine, I'm trying to start up an industry, I'll be making Panadol. At least I've been to Famanova where we made Panadol. Then that Panadol has to be tested by Zambia Bureau of Standards. And then you work in the lab, they bring you those samples saying, no, we have made quite a number of products. Now, we want you to certify them if they are set, if they are okay, if they're up to the standards. So they bring them to you, then you are working on them. These are some of the things that will delay. Even when you're writing a lab report, you can bring them out, say, I was delayed because of the temperature in the machine, or maybe because of the solubility of the sample that are present, the solubility of the components present in the sample. We can say maybe because of the boiling point of the sample that I was working on. These are some of the things that you can bring out in your lab report. The detector. Now what? I think now we're done. We're done, we're done. How it's done? We are done. Now we've gone to instrumentation. Suppose you work in the lab and then they tell you that the detector is not working. What type of a detector do you buy? What type of detectors do you buy? And that's the point that we've gotten into. So now about instrumentation. So saying that a several number of detectors that are used, and the common ones is that one. Now here, I'm afraid you need to know them. At least just give examples of detectors. It may not really mean you explaining yourself, exculpations of how it's done and that and that. Here, it's just important to give the names. Unless when you are doing analytical, and should be instrumental. Where do we find this? We were using this in instrumental, no, in analytical spectroscopic method of analysis, and particularly the instrumental method of analysis. That's where we're doing a lot of instrumentation and how they are used. Those guys would stress us. Yeah, so these are the ones here. So these are the ones that can bring out one. We've got a flame ionization detector feed. So that, just know that. Yeah, I think for this course, analytical, no, unless the 2112, yeah, 2112, that's where you do a lot of this. So just know them that there's flame ionization detector, there's nitrogen phosphorus detector, there's flame photometric detector, and then there's mass spectrometer detector, there's electron capture detector. Wow. Though these ones again, just look at the names. Flame photometric detector. This one is it's coming from a separation technique which we call flame photometry. Flame photometry is an analytical method that we use to, I've used that method before, that we use to detect the presence of ions in water. Yeah. I remember the water we're working on, I think, was Manze Valley. Yeah, we had Manze Valley, and then we're trying to detect the presence of the amount of sodium, the amount of chlorine, the amount of, just look at the bottle of water and then look at the nutritional content there, the ingredients rather. Yeah, those are the things that we were determining, and the method we used was flame photometry. So yeah, that is one thing that can guide me if I'm to study that. So there's flame photometric detector, there's nitrogen phosphorus, flame ionization detector, and then there's mass spectrometer detector. Mass spec is also one of the separation techniques that we have. Mass spec, we have infrared spectrometer, we have Raman spectrometer. Yeah, those are some of the methods. Then electron capture also is one of the methods that we use in the determination of components. Yeah, so just know them, just know them. Then those are things. So closed, you can have the flame ionization, we've got nitrogen, we have the mass spectrometric detector, we have electron capture, and then we have flame photometry. Now, these are some of the things that I think this is just for the sake of understanding. That's why I didn't even highlight them. This is how it's done, the detector, but I think it's not important. Yeah, so now how do you interpret the output from the detector? How do you detect the peaks? Because this is important. That's why I highlighted it. How do you now interpret the peaks? So saying the area under the peak, the areas under the peak are the proportion to the amount of compound which has passed the detector, and these areas can be calculated automatically by the computer linked to the display. This now there are two things here. There is a method that we use in the. There's a method that we use in the. There's a method that we use in the lab, and there's a method that we use in the industry. When we were in school, we were calculating these things by ourselves. But when you're in the industry, the computer does for you. Because there you are learning, so you have to learn manually how to do it. Find time to just to check the infrared spectrometer of water. You're going to see a lot of peaks like waves. How to interpret that? We were doing it ourselves, but in the lab, of course, the machine has to do it for you. Okay. Yeah, that's the point. So that's the thing. So the area under the cave tells you how much the sample is present, the area. And then the number of peaks tells more about the number of components. So this is now the instrumentation that we need to understand. So we've got halfway the document. I think we won't finish. Yeah, won't finish. So I'm saying that this is the instrumentation. You need to have some source of the inert gas. So the inert gas is in the gas cylinder. And then now we have the injector, we've got the flow regulator. This is what regulates how fast the inert gas carrying the sample is flowing. And then we have the injector point here. So the sample is injected from this point. And then this column, like it's long, it can go even to about, some go about, some are long, about 15 meters. It's very small, but it's coiled, yeah. And then we have a detector here, and then we have the recorder. Mostly the recorder is the screen of a computer. Yeah, so that's the instrumentation from the few things that we were discussing. Let me see where we can end from. So we're saying that, okay, where do we use this? We're saying one, we use it now. The application of gas liquid chromatography, that's what we're looking at. The application of gas liquid chromatography, one in the pharmaceutical industries. Yeah, I've done that before. So we're saying gas liquid chromatography is used to analyze the residue solvents in both raw material, that is, if we're talking about drugged up substances, as well as the finished products. We are able to tell the amount of components that are present in there, because we are avoiding a situation whereby someone makes Panadol and then he or she includes the stones, which are not important in the healing of the body. So you have to make sure that the things that are present in the drugs are those specifically meant for curing a specific illness. We don't want to have a situation whereby you've healed the headache, and then the stomach upsets set in. We don't want that. So we avoid that. We need to make sure that we produce pure drugs. Then the other one is a food flavors and the fragment fragrance. It's more or less like food producing industry. You have to make sure that the food that we produce is up to the highest standard. That's one way in which we use that. Of course, even in analytical industries, we've been using most of these. Yeah, and then the other one is petrochemical and all that. So that's it. That's it about gas liquid chromatography. Now we can go to ion chromatography. I think for now, we'll end here because this is a different component. Yeah, this is a different component. I think it's just important that we end here. So this is how it does the detection. Yeah, it's just important that we end here because it's not good to learn a lot of things and then you forget. So it's just important that we end here and then we see how far we can recall. All right. Like I said, in case you want to hear something from me, you can reach me on 097-5578-694. You can find me on YouTube. just search for Kundamulenga. Yeah, those are my details. So goodbye for now and enjoy the rest of the day. So where do I go? I need to cancel the recording before I